all. This is Dr. Mobeen Sayed from drbeen.com. Welcome to one more show. So this is our second part of Professor Resia Pretorius's work from South Africa and her team's work. We have done the initial talk about her recommendation, her pathology that they observed, and I'm going to show you that they actually saw those pathologies, diagnostic approach they have observed, and that needs new equipment, and then management approach. So now we are going to go deeper into what they were seeing. It is a fascinating world. Plus, I think that long COVID is the problem at this time that we'll have to handle. COVID is almost out. So, how do we handle long COVID? There are two types of long COVID issues. One are the sequelae of the diseases. So, somebody's lung got damaged and now their lung is shrunken and they need oxygen and they need rehabilitation and they need exercises and the physiotherapies. That is a different issue, for example. Similarly, let's say somebody's pancreas got damaged and now they are getting diabetic a little earlier. That's a different issue, cardiac issues, and so on. This is a continuity of the pathology, that is the vascular and clotting pathology, which then causes tissue damage on a regular, longer basis and needs to be stopped. Otherwise, they can cause permanent issues, permanent damages. So let's look at her work. Very important work. I'm going to reach out to her to see if she can join us. I hope she joins us. So here it is. This is her article, Resia Pretorius, and the article I just showed it to you before. I have opened up her papers here, many papers. So let's start from this one. First is TEG, microclot and platelet mapping for guiding early management of severe COVID-19 coagulopathy. Imagine what she's saying is at point of care in the clinics, hospitals, there should be platelet elastography machines. And we should not only look at the bleeding times and D-dimers and CRPs, but we should start as soon as the patient is getting COVID, we should start looking at the profile of the platelets to see how badly they are pathological. And if they are becoming bad before D-dimer goes up, she says we should start managing the patient based on how the labs are looking. So let me show you. So if you see here, a multi-pronged approach guided by TEG. TEG is thromboelastography, and I'll show you what does it measure in this paper. And platelet mapping would be required to maintain normal clotting physiology in severe COVID cases. Then I'm going to go to first show you parts of TEG. And this is all her work. This is her copyright. So if she said take it down, we'll take it down. Table 2. This is their thromboelastography clot parameters for whole blood. So let's say a patient of COVID, their blood is taken. What are the kind of things that are going to be seen in TEG? And the point is, normal other lab systems and the lab markers will not provide a signal right away. This would help. So for example, it has an R value, reaction time measured in minutes, time of latency from start of the test to initial fibrin formation. That's one. Kinetics measured in minutes, time taken to achieve a certain level of clot strength. Alpha or angle, the angle measures the speed at which fibrin build up and cross-linking takes place. Remember that fibrinogen is a product, you can say that is a raw material for the rope. Then that rope is converted, if I can draw as well. So imagine there is some raw material. This is called fibrinogen. When the clotting is needed, then what happens is this fibrinogen. So whenever there is a ogen somewhere, that means creator of. So pathogen, creator of pathology. Fibrinogen, creator of fibrin. What happens is, this is the fibrinogen, And then there is thrombin, a clotting factor that would come in and kind of make it into fibrin monomers. We have done this discussion in the past. Then many fibrin monomers would come together and then they are kind of bound to each other and they take part in the clot formation. Then the plasmin would come and cut them, and then these would make D dimers. So, this is the life of the ropes in the clot. So, here the fibrin buildup, they're talking about this part. When some area of the blood vessel is broken, whenever tissue is broken or injured, blood vessels in that area are broken as well, or injured, or opened, or breached. So, here, let's say this is an area of the blood vessel that is damaged. Whenever that damage would occur, that would start the fibrin deposition over here, and that fibrin deposition is clotting or starting the clot. It would get platelets trapped in it, and then the clot would build up. So fibrin build-up speed is what the alpha angle says. Then there is MA, maximal amplitude measured in millimeters, maximum clot size. Then maximum rate of thrombus generation, how fast the thrombus is being generated, time to maximum rate, and so on. There are a lots of values in this testing system. So once you use this machine, it would come back and say, here is the data. And then in this paper, if you are a healthcare professional, I would recommend that you read it. If you are a person who is not a healthcare worker, but you are concerned, then keep it with you. Or if you know someone who has long COVID, then send it to them so they can discuss with the doctor. Then he or she has, and that team has mentioned that which markers is more interesting to see and what kind of then response should be there. What I want to show you is this. This is the fibrinogen becoming fibrin and then dissolving. And they're showing this is a normal healthy fibrin and this is unhealthy in COVID. You can see the difference between them. Then, if Doug is here, he would say my mouse is quacking. Look at this. So if I go down here, it says fluorescence microscopy showing microclots in platelet poor plasma. So this is plasma that doesn't have platelets in it. Even then clotting is occurring because they put spike protein in it. So spike protein itself is such a, I was reading these papers and I've throughout the 1.5 year, I've been reading various studies, and I was thinking that this SARS-CoV-2 and this spike is such a perfect poison that it does so many things to us. Every day we find out something new. Although this was about a month ago. So fluorescence microscopy showing microclots in platelet poor plasma with representative examples of the different stages of microclot formation. So as you can see, they're starting from here and it just keeps going. And what they say in the writings is that the clot that is formed is resistant to lysis. Lysis means breaking it down. Whenever we make a clot, we break it down. Whenever we start inflammation, we stop it. Our body is always uh, in a state of balance. That is why we say we like homeostasis. We like a state of normalcy. So here, this clot is refractory or resistant to lysis, to breakdown. That can be a big problem. Then this one is the fluorescence microscopy examples of the different stages of platelet activation and spread. So when a platelet becomes activated, then number one, when it is activated, it releases calciums and other things, and it opens up its own receptors to bind with other platelets to hug them. So that is activation. Plus, it spreads over the area. So imagine if we take a band-aid and we kind of spread it over the wound. Similarly, these microscopic plates would start spreading out. So as you can see, these guys are spreading here. Then this is the clumping, platelet clumping together. And if you see here, this is happening. So fluorescence microscopy examples of the different stages of platelet clumping with no clumping occurring in the healthy control progression to severe clumping of platelet is seen in stage 1 to stage 4 with a score of 1 given no clumping. And so in healthy people, there is no clumping. But if you put spike in it, then the clumping starts occurring. So this is one set of diagrams. I want to show you now this. This is their beautiful work. This is the spike protein S1 induced fibrinogen resistant to fibrinolysis. S1 caused clot that is resistant to breakdown. Implications for microclot formation. So see, if they're saying here SARS-CoV-2 spike protein S1 subunit as potential inflammogen sui generis. Potential inflammogen produces inflammation. Sui generis, a class of its own. It doesn't need anyone else to help it produce inflammation. It itself can cause inflammation. So using scanning and electron fluorescence microscopy as well as mass spectrometry, we investigated the potential of this inflammogen to interact with platelets and fibrinogen directly to cause blood hypercoagulation. So I want to show you the pictures. And as you can tell, I spent the whole day reading it and marking it. I cannot remember anything which I do not mark. So here is a spike protein. S1 unit is the poison in it. And what they're showing is amyloid protein and anomalous clotting in platelet poor plasma samples to study spontaneous anomalous clotting of fibrinogen in the naively healthy PPP samples. So the blood sample or the plasma sample doesn't have platelets, should not clot, but you put spike and suddenly it clots. Anomalously it clots. It clots incorrectly and suddenly. So the pictures of that, as you know that I like pictures. The second thing that they're showing in this paper is microfluidics. That is the flow in the presence of these clots. That is the flow impact that would happen to us as well when these clots are present. So let me show you the pictures. So fluorescence and sorry, microscopy of the purified fibrinogen and PPP. So I'm going to go here. Look at this. Fluorescence micrographs of purified fluorescent fibrinogen. Fluorescent fibrinogen with thrombin, here A. Fluorescent fibrinogen with added spike protein. Almost we can read it as added poison. So this is the fibrinogen with thrombin. So thrombin's job is, so this fibrinogen, to convert it into fibrins, we need thrombin. You can say thrombin helps start making the ropes that are needed to bind the platelets together. So without thrombin, we cannot start having a good clot. And once that those ropes are formed, then they are put together tightly, and then finally they are broken apart by plasmin. So what they're trying to show here is that if you take plasma and you put thrombin in it, then thrombosis would start, correct? That's a normal behavior. If you take plasma and put thrombin, thrombosis would occur because thrombin would activate fibrinogen or convert that to fibrin, and then the clotting process. That process does this. This is the normal clotting. This is clotting A. But if you don't put thrombin and put spike protein, then that is this B. Look at the difference, how potent of a clotting starter the spike protein is. Look at the clot it formed. The whole thing looks like a clot. This is the normal clot. This is clot as well. It just blows up my mind to see this. Okay, so this is healthy platelet poor plasma. So this plasma from a healthy individual, it doesn't have platelets in it. That means it would find it difficult to make clots because platelet are the bricks that are in a clot. This is healthy platelet poor plasma plus spike protein, and the clot started forming. This is healthy platelet poor plasma with thrombin. That is, you put something in it, there is no platelet, you put thrombin to say, okay, make ropes. And those ropes help make this much of a clot. What are they making clot with? There is no platelet. So they're kind of looping in other molecules of fibrin. They're looping in maybe RBCs or whatever tiny aggregates they can make with the other proteins. Here, platelet poor plasma with spike protein plus thrombin. Look at this. And now if you put platelet on top of it as well, which is a normal state for all of us, think what would happen. Okay, so look at this one. Fluorescence microscopy, micrograph of platelets before and after exposure to spike protein. This one, A, is platelets just roaming around. So you are picking them up with fluorescence. You put spike protein, and this is what they do. Clot, clot, clot. So these pictures that you're going to see now are fascinating. So this is scanning electron microscopy and WB, or white blood cells. So check this out. This is healthy individual. This is scanning electron microscopy. So what they do is they take cells and they kind of freeze them with a spray of electrons on them. So they almost freeze them in metal. And then they take their pictures, they put light on them and take their pictures. So this is what is healthy cell. I'm sure that this is a RBC. This is a normal platelet. Check this out. This is a platelet that is exposed to spike protein. Do you see this little, I hope I can make it bigger. Do you see this little membrane spread out? So platelets don't have a nucleus. So down here in the center, it's not a nucleus, it's just a bag. Platelets carry glue with them. So this is that bag. But look at their membrane, how spread out it is. And look at this side. Do you see the spread of the membrane? This is under the influence of spike protein. Platelet is spreading out as much as it can. It is too much activated. And look at this. In the presence of spike protein, unnecessarily, the clotting, see this little trash like threads that you're seeing? These are fibrin threads, and they're trapping the cells in them. And look at this. So these are fibrin threads that have come together and they're trapping RBCs in them. And these are the clot formed. And these clots have RBC stuck with them. They would also have platelets stuck in them. And imagine this little rough thing. You are dangling it inside the blood. So more RBCs passing by would get stuck, and more platelets would get stuck, and more fibrinogen would get stuck. This is just going to cause problems. So whole blood sample of healthy volunteers before and after exposure to spike protein. So the person was not exposed, their blood was exposed. This is microfluidics. That is what I shared before. This is a normal, healthy, platelet poor plasma. When the fibrinogen is activated, I hope we can see here, this here on the, so these two black lines are actually, this is a tube in which there is this fluid plasma, but it doesn't have platelets. So in a healthy person, if you see here this little aggregation, that is what fibrin strands are doing. Then here, I do not know if you can see this little very light structure here is the little flap of that clot that is formed. So this is all healthy. Look at this. You put spike protein in this, and look at this trash over here. This is all clot without even platelet. This is just using cement to make this without even bricks. And look at this clot, this guy. And they say that it does not wash away and it sits in the center of the stream, so it disrupts the fluid dynamics. So not only it causes blood vascular damage by sticking to it and causes physical obstruction by reducing the lumen or sitting in the lumen. Lumen is the internal hole of the cylinder. If that's what we call it, we call it lumen, right? It's obstructing the lumen. Not only that, it is actually dangling and floating in this. So it is causing fluid dynamics issue. And then they have some pictures of the cells here, that's another paper here. I think this one. Erythrocyte, platelet, serum, ferritin, p-selectin pathophysiology implicated in severe hypercoagulation. So here what they're saying is that this hypercoagulation, the things that are taking part in it are blood cells, erythrocytes, serum ferritin. So whenever our cells get damaged and whenever we have infections, we try to increase, uh, we try to reduce the serum iron because our body knows that pathogens like to use iron to build themselves. They need to make DNA. For that, they need iron. So our body hides the iron in macrophages and stores them away. But whenever the cells are destroyed, iron would leak out. So the iron, p-selectin in hypercoagulation. So p-selectin, what is that? Yesterday, when we were discussing the lecture, we were talking about, let's say this is a blood vessel. In this blood vessel, of course, the sides have endothelium, which is the cells that make up the walls of the blood vessel, inner side, inner surface. And we discussed that imagine if there is a inflammation here in the tissue. That inflammation causes the local macrophages and dendritic cells and other cells to become active. When they become active, they release chemical substances, chemokines that go into the blood system as well. So when the platelets and other things are passing by, neutrophils, other white blood cells, when they're passing by, they look at all of these chemical substances and they say, you know what, I should get out and help. This is a signal for me. So now these guys are just zipping by. How do they slow down and get out? So we call it margination. Margination is when they go down on the margin of the blood vessel. Then we call it rolling. They roll on it. Then they stop and then they get out. There is margination, rolling, and then getting out. For that process, how do we stop these ships? We have adhesion molecules or little pieces of glue on endothelial surfaces, and these cells that are here and they have thought that I need to get out, they would also extrude their own cell adhesion molecules. These are called selectins or cell adhesion molecules, selectins or CAMs, CAM. So there are p-selectins and various kind of s-selectins and so on. So what they're saying is endothelial cell, erythrocyte or RBC plus selectins, they are the ones that cause the pathology with iron. With iron. So that's the basic recipe for hypercoagulation. So this is also a beautiful lecture to read, I want to show you the pictures. So once again here, I think now you can make out this is healthy, this is less healthy, and this person, oh, sorry, this plasma has ferritin or iron plus spikes. And look at the aggregations. But look at this here. So now are the great pictures. Number one, representative scanning electron micrographs of the erythrocyte. So this is erythrocyte and platelet ultrastructure. Actually, here we cannot actually see it where this arrow is. Down here is a platelet. There is a little spread out rug. That is a platelet here. And then here is the platelet. These are how platelets look. And they're saying that why are they activated? Because they look like they're spread out. Normally, they should not be spread out. They're saying that they're spread out because they are on a glass surface. And for them, the glass surface also is a clotting factor. Remember, if let's say we are injured and there is a glass material that injures us, that would start activation of the clotting, iron, any foreign material. So here, because these platelets are sitting on a glass surface, they're taking that as a clue to say we should start becoming active. So this is the activity that they're showing. Now check this out. Here, these are the RBCs and platelets. These spread out guys with these little tentacles are platelets. They're becoming active here. And they have these, of course, the fibrin will be there as well. Here is a platelet that is becoming active and spread out. Here, do you see this is damaged? Do you see a crater in the surface of the platelet? So the poor platelet got activated and it became so activated, and there are so many inflammatory system molecules here that the platelet itself got damaged in that process. This is spike triggered. Here is another platelet, and that has its own damage. All these yellow markers, arrows, are actually the area of damage. So here is another crater in the surface of this platelet. These platelets are totally damaged here, their membranes. Look at this big hole in the platelet. They are damaged platelets because of the spike proteins. Then look at this. This is, I believe, erythrocyte. These disc-like things are red blood cells, and these cloud-like things are platelets. So this is the platelet and red blood cells interaction. So when you put the spike protein and activate them, they start clumping to each other as well, and they'll clump to others as well. So this is like if you go to a mall and then the people in the mall just become active and everybody starts hugging each other and they start making a huge big cluster. This is what's happening here. So you can see them attaching to each other. So representative scanning electron micrograph of the interaction between erythrocytes and platelet of a COVID-19 positive patient. Then this, look at this. This is a red blood cell. These are platelets. Do you see that they are connecting here? This part, this part is shown in detail close up over here. And do you see how they are? Bambi, I'll look at your question in a second. I'm just so enamored by looking at this. Do you see these thread-like structures that are bound to each other? These are cell adhesion molecules. These are selectins. And they're saying that spike protein causes abnormal activity of selectins and things start fusing with each other. Look at this. This is also another red blood cell and another platelet. And look at this. This is the paw. This is one of the tentacles of the platelet, which is attached to the surface of RBC. And here is the close up. 200 nanometer close up. And look at this little paw stuck to this RBC. They start sticking to each other. And that's the clotting. Look at this here. Look at this. And look at this one. If I go to the top, this is an RBC, red blood cell. This is a platelet which is activated. Do you see all the spread out part of it? And here is the close up of how it is interacting with RBC. Same thing here as we just saw. Look at this. This is now the fibrinogen becoming active, the threads, the meshwork, the network of molecules, they are becoming active and they're trapping the cells in it. So this is, if I go to the top here, so this network, I hope you can see it. This network is all fibrinogen threads. And these are little cells and platelets that are getting stuck in it. And this is a further close up, and you can see how vast the network has become. And the cells and platelets are getting stuck in it. And look at this. These things, these clock like things, they are RBCs. And here they're stuck. Look at the close up. Look at this mushy, sticky thing that they've made. How would we get it out of the blood vessels easily? So the solution is don't let it happen. Here is the RBC with all this clotting stuff on it, the fibrinogen on it. And here is the fibrinogen. This is also RBC with fibrinogen. This is RBC with fibrinogen. So the point is they're saying it's not just the platelet that contribute making in these clots. Here is RBC taking part in clots. And this now the problem of these clottings, think about it. It's not just that, fine, there is a clot. The problem is that wherever these guys are stuck, they're going to obstruct that blood vessel. That would cause reduction in the nutrition to come to that tissue. That would cause reduction in oxygenation. That would cause hypoxia. That would cause damage. Similarly, tissues, when they're functioning, they produce raw material or trash, not raw material, they waste material. That waste material need to be washed out. They also produce carbon dioxide that needs to be taken out. Otherwise, the environment will become too acidic and it would kill the tissue. And now the whole system is jamming up in the smaller blood vessels. So those tissues that become victim of it, they are going to die. If they die, then that is a permanent damage in some cases. Then they talk about the viscosity, and then finally they discuss how should this be managed. Then this is the roller coaster. This is another paper they have. I would let you read this, but what they're saying is the following. There's a picture that is interesting, and Dr. Paul Merrick has discussed this with me as well in the past. I have myself discussed it 1.5 years ago. Actually, it is so funny. Remember when vaccines were newly started, and there were reports of clotting from UK, and there were a scientist from Germany who said these are microclots. I presented that data. I still remember that was the first time I said something that people did not like and thought it was I was bad mouthing the vaccines, which I was not. Now it is all clear here. And I got the heat for that. And in there, I had explained that why thrombotic system, a system that makes clots, reaches a point that it cannot make clots anymore and causes bleeding. So the patient first is making more clots and damage because of that. And if that continues, then the bleeding starts occurring. So that is the paradoxical situation, that on one end there is more clotting and then there is more bleeding, the problem is the same. So here is that roller coaster. I discussed it. I believe this was December or January of the December 2020 or January 2021. Here is what happens. This is the normal blood system. And let's say there is one von Willebrand factor, which is the blood clotting factor, I believe, number 8. This is P selectins, or the cell adhesion molecules. These are D dimers, which are the byproducts of broken fibrinogen strands. These are fibrinogens. So you can say this is clotting occurring, and this is abnormal because the raw material, the fibrinogen, the van Willebrand factor, the selectins are available. But as the thrombosis occurs, it would continue to consume fibrinogen, and liver cannot just keep producing at a very fast rate. So at some point, liver cannot produce more, and the one that is already present has been eaten up. When that happens, our body cannot make further clots, and we need to make clots. For example, I gave this example, I remember, if I do this, there are going to be many small blood vessels, capillaries, that just got punctured, and I am going to bank on the clotting system to go and repair them or close them. So imagine if I don't have that raw material anymore, then I'm going to start bleeding. So it become easy to bleed, and it can cause lots of damage. So that is a roller coaster, that in the beginning there is tendency to create clot, and when the raw material is eaten up, then there is a tendency to bleed. So this is why we say thrombocytopenia, thrombotic thrombocytopenia causes clotting and causes bleeding. So this is that they're talking about. And here they're talking about, this is fibrinogen, then thrombin works on it and causes fibrin formation, then factor 13A works on it and makes them more strong, then plasmin works on it and breaks it down, and from there D dimers are formed. We have done this discussion in detail in the past. So these are the works, beautiful works, to me, just like Dr. Bruce Patterson's works, and he is also honing on spike protein. And here is another set of works that is interesting. Okay, so sorry, I was just continuing to go there. Now I'm going to look at the questions. Bambi, you had a question. I remember I looked at it. That question was, if the iron. So let's see, your first question is here. First question from the latest questions. So will that also make the MCV, mean cell volume, on a blood test big, macrocytosis? So macrocytosis would occur if the cells are bigger or the relative size of the remaining system is shrunk. So, or if there is, for example, more iron and we have less iron, which would cause megaloblastosis, which means less iron or less folic acid, for example, or less B12, for example, they hamper with the cell production or cells' essential material production. So the cell just keeps becoming bigger and bigger while the brain is being built slowly, and the cell becomes big. So yes, there can be changes in the cell markers. I think that you're trying to figure out that other than TEG and scanning systems, what are the other markers that might point to this. Freelancer says clotting due to S1 part of the spike protein. Yes, that's the discussion here. Ramnik says they look so big. Actually, can you imagine that we can actually see that detailed? And not only that, I had shown this in the past when some folks say that, hey, have you ever isolated the virus SARS-CoV-2 electron microscopy? I actually once played a video of SARS-CoV-2 where they had actually These are all SARS-CoV-2 images. This is SARS-CoV-2. These are the green things are the spike proteins outside. This blue kind of greenish thing here is the envelope. Inside is the remaining structure. Remember this one? We actually went over this, and this person, their work was they had slices of the SARS-CoV-2, so you could see the slices of it. That was just crazy. So virus isolation is one thing. We have the slices of the virus. This is SARS-CoV-2. New images of novel coronavirus SARS-CoV-2 now available. NIH, allergy and infections. Let's see, what do they have here? Slow computer at this time. So here, the scanning electron microscope image shows SARS-CoV-2 yellow, also known as 2019 nCoV, the virus that causes COVID-19. Thank you very much. So here, these yellow guys are SARS-CoV-2. And these guys are SARS-CoV-2. Can you see them? These little things are the ones that are causing issues. Okay, anyway, sorry. What were we talking? So is it known what's activating the fibrinogen growth? That's what we just talked about: spike protein, iron, and then red blood cells and platelet participate as well. So this is a good question. Richard says, how long do these clots stay in the body post-infection? So they keep breaking immediately. That is why you start seeing the D dimers. So they form the break, immediately. However, if these pathologies continue, let's say because of the, in my opinion, autoantibodies that act like spike protein could do the same things as well. And remember that cell trend Sean had mentioned? Cell trend profile, the cell profile can actually identify autoantibodies. So, and it is so interesting. I had actually invited their CEO or someone, and they said, yes, we would love to come in. And then we kept asking them, and they just became radio silent. They are from Denmark. Actually, we reached out to the Denmark's epidemiology head as well, who worked to lift the, what is that, their lockdown, and she refused to join us as well. Oh well. Here, how long they stay? If the pathology continues, then the clotting continues to occur, and in some cases, it keeps going for months. So when the ferritin leaks out, so ferritin is present and it is mostly in the normal state. And so ferritin is a part of this clotting mechanism. So Vash says, how common is this, and is it a normal occurrence with a COVID infection too? So of course, if you can see, the prevalence of long COVID is, I mentioned it before, so I'll just put that in front of us here, 43%, or from 35 to 63%. In hospitalized patients, 57, 45 to 68%. In women, more. Then they have various regions here. For example, Asia, 44, North America, Europe, 30, North America, sorry, so I should read it this way: 49 for Asia, 0.44 for Europe, 44, 30 for North America. Global pooled prevalence is 30, 60, 90, and 120 days after index test positive date were estimated. So anyways, here is the possibility that for many, many days, many months, in 20 to 30% of the patients at least, this can happen. So it's not, so in those folks, this is probably continuing for some time. Otherwise, normally a person who got the infection and recovered, it happened and it went away. Cool. So friend had Delta a few months ago and a recent surgery where she couldn't clot. Recent surgery. I don't think that I can. If she had Delta and she recovered and there were no other issues, then this is not related. Must be something else. So again, the labs can tell. I'm just making a conjecture, uh, which I should not. So labs would actually help them figure out. GTO says dogs here. Now Luffy keeps me awake in the beginning of the night and in the middle of the night. So he is going to keep doing this till. And yes, I know I should get a catio. I will get a catio. He's going to keep doing it till what, 10 o'clock? Then he'll go to sleep and wake up at 2:30 and do this again. So Emily says, with the iron involvement, what would iron deficiency mean for the fibrinogen? So if I go back here to their iron, maybe with the interest in iron, I should um, do a separate talk about it. Um, am I in the correct study? The roller coaster fibrin, so that is roller coaster. This may be the one. Erythrocyte serum ferritin. So if I go to iron, so strongly associated with COVID-19 coagulopathies is the presence of hyperferritinemia, more ferritin, iron and serum ferritin, a marker of oxidative stress, in circulation can act as a marker of damaged cells. Excess circulating iron has long been known to cause blood to clot into an anomalous form, later shown to be amyloid in nature. So they're saying that if there is extra iron, where did the iron come from? Because of the cellular damage. When the iron is more, it changes the clotting structure and make it anomalous or incorrect, and the deposition of amyloid start occurring in it, so the clot become more sticky and difficult to break. Both platelets and erythrocytes also show pathology in the presence of increased iron and serum ferritin. Hyperferritinemia is also known to accompany ultrastructural changes in both platelets and erythrocytes. So the platelet itself and the erythrocytes shape. Remember, I had done this discussion. There was a study that said that people in long COVID or patients of long COVID had blood cell shape changes, which was contributing to the clotting. So here you are seeing that as well. So actually, all of these things connect together. S1 or spike is the basic anomaly. So S1, the macrophage activation can occur as well. Mast cell activation can occur as well. S1 is now sticking in the monocytes. S1 is also causing clotting. That is also causing the damage, is also increasing iron. Iron itself is changing the blood cells shapes. Plus, iron is instigating incorrect clot formation. So here, iron can also leak into the circulation due to cellular damage to not only erythrocytes but also endothelial and other cells. Both iron and serum ferritin may result in Fenton reaction, oxidative reactions, that may drive oxidative stress in circulation, which would cause further damage to the blood vessels as well. And that's about the iron. I hope that answers that question. Uh, Ideally not. So Michael says, would microclots cause lymph nodes to swell? No. Lymph node swelling is a normal process. In some people, it happens more, in some people less. But that is a normal process because lymph nodes contain the B cells and the T cells. When there is an infection and the pathogen is carried, or broken pieces are carried to the lymph node by macrophages, or neutrophil eat them up wherever they chew them up and throw their pieces that are washed in the lymph going to the lymph node. Then inside the lymph node, B and T cells start proliferating. That causes the swelling. So unless there is a pathology of the lymph node itself, this swelling is because the immune cells are becoming active and more in number and bigger in sizes and secreting stuff, and that causes pressure. Lymph node has an external cover on them that is tight. It cannot expand. So whatever swelling occurs, it cannot go beyond that, and then it becomes painful. And our body's behavior is wherever there is inflammation and repeated inflammation and damage, our body puts calcium there. Calcium is like our cement to fill damaged things. So if a lymph node continues to become inflamed again and again, then it would become damaged and the calcium will be deposited, and that is why it kind of becomes hard. John Doe says, I would be interested in a talk on iron versus zinc, copper, and other minerals. I think we can do that. Lindia says, Dr. Bean, should we take low dose of aspirin to prevent these clots? So, Lydia, you know that I cannot say that. So, this is something that you have to talk with your doctor. When I was going through the vaccine process and then later on through the COVID, I made sure that I took the aspirin. A baby aspirin in my age is just generally recommended. It's available over the counter as well. Plus, aspirin during this disease process for inflammation is recommended as well. So at least I had taken a little more than the baby aspirin. So Tech Ads says, does the S1 trigger clotting even when there is no damage to the endothelial tissue? So that is what they're showing. The tests that they are doing, there is no endothelium there. They're just doing it in test labs, and S1 is causing clotting even without platelets. Strangest thing, this virus and its parts, especially the spike. And Denise says, Catio fund for Luffy. Thank you for listening. I have listened. Yes. So it is possible that the bleeding times and the clotting times will change. Yes. The thing is that they're saying that before a lot of changes become evident in normal labs, the platelet and microclots start becoming observed, and labs are not yet abnormal. And they say at that time we should figure out what's happening. And if at that time, when the other labs are fine, bleeding times are fine, and we still find the markers for the clotting, we should start managing. I think this should just become part of the normal protocol. But the problem is, normal protocol only starts when somebody becomes severely ill. These authors say when D dimers and CRPs go higher up, then they have already become so ill that their chances becomes poor. Prognosis is poor. Celtic says, did Dr. Bean just say he's going to get a catio, catio for Luffy? He needs something. I am. So when we had my son's younger newborns, my wife will be awake all the time, and I used to think what a hard um, work it is. Now, Luffy keeps me awake like my wife used to be for the children. So, Dr. Bean, you read anything significant drops in hemoglobin from COVID? Possible because number one, the bone marrow cellular processes can be disrupted. Number two, the RBCs themselves can be disrupted. Number three, the manufacturing of the things because of the abnormalities in the supplements and the vitamins and the raw material that is necessary. There can be an issue with absorption of the raw materials as well. As draw from 11 to 8 in a month. Normal and not blood and stool. Yeah. So it must be absorption related issues. I hope that they're managing her. Tex is a soundproof cat here. I actually like his, I mean, not this whining all the time, but I like him interacting. He's very interactive. Meeple art, this is a good question. Does the spike fusion in the vaccine mean less possibility? The S1 part is it doesn't need fusion because it's not that the spike has to be cleaved to expose S1, it's always there. So, unfortunately, if this happens, it would happen with spikes. So, Zach, what I do not know is in a vaccine, the let's say Novavax, that spike protein is kind of stuck in a bouquet and then it is picked up by macrophages and destroyed and structured that way. So more of a possibility of having that S1 get stuck in the monocytes than S1 running around and causing issue in the body. But can Novavax's spike protein escape everywhere and cause a damage in that tiny amount? That I have to see their blood clotting and myocarditis, and that would give me an idea. I was supposed to look at that today, but we started Alberta yesterday. I deviated from Alberta and did this talk because I thought this was important. So now I'll see tomorrow if I can look into that. So, so Michael says, is this data applicable to Omicron? Would vaccination be likely to reduce this or possibly also cause this? Finally, is there a mechanism for lumpectomy to help? So, is this data applicable to Omicron, at least from a mechanism point of view? Yes. The would vaccination be likely to reduce this or possibly also cause this? So, here is the mechanism that I have been discussing, and it may or may not be correct, but here is how there are some folks who are long haulers, and vaccine actually helps them. Now, we do not know, just like we do not know which with COVID who will be injured or die, we also do not know with vaccine who would get lingering effects. Similarly, we also do not know which long COVID will be helped by vaccine. I think a way to know that is the following. If a long COVID patient is continuing to make anti-ACE2 antibodies, and that is the cell trends. It's so funny, I keep talking about their system, and they somehow became scared of coming to my channel, maybe. That they were very excited, just, yeah, we want to come in, and then they just stopped responding. So anyway, cell trends does this test, and I have no financial relationship with the current anyone I've discussed, no financial relationships. So cell trends, anti-ACE2 antibodies. Anti-ACE2 antibodies would look like spike protein. So if somebody has them and they have the symptoms of long COVID, then they would benefit from vaccine, because vaccine will create antibody against the anti-ACE2 antibody, and that would clear it out. So that is one. Now, so could vaccine reduce it? Yes, but in some people. Can it cause it? Yes, because it also has spike. Now, how much spike? Where does spike need to go? How big of the inflammation? That is all up in the air. Finally, is there a mechanism of action for lufumectin to help? So, same thing. That help is mostly with the receptor binding domain. That is not helpful for the S1 piece. And this problem is because of this blue area, the S1. And so lufumectin cannot do much there. It binds here. Unless it's S1's pathology that it is causing, that we're studying today, is because of the RBD part of the S1. RBD is part of S1. So if the pathology is because of the RBD, then yes, lufumectin would help. And that may be the reason that some folks with the long COVID or vaccine uh, side effects respond to lufumectin. Indiana SB says here, see above. Okay, so see above. Above is Texas, saying Michael Yippee Yahoo. Thank you, Texas. Indiana, do you have a question up here? Louis Grande has a question. The fact that we can't openly discuss possible steps to ameliorate this phenomena and ask questions is such a low point for science itself. Weird times. Absolutely. And as I think that you're a medical student, when you come and your generation grow up and be in the position of decision making, please see the current decision makers and don't be like them. We are not setting a great example for the next generation. So please don't be this generation then at your time. Colombian coffee bean is additional spike protein needed for the clot to continue to grow. So just 1 second, Colombian. I want to add more to uh, Luis's question. When this pandemic started and we were all locked down, essentially there were no cafes anymore, there were no parks anymore, there were no places to meet and discuss things anymore. So these places like Twitters and YouTubes and uh, other, these became the modern day cafes and coffee shops and meeting places to discuss. But the way they behaved is unacceptable. So when governments used to run these kind of communication systems, then we were afraid that they would cause propaganda and they would be government side, government talking, people who are just saying yes to everything government is doing. So the privatization was supposed to be a great thing. And here we are seeing such a rotten outcome of the privatized media and pharmacies, and others. I am still shocked that Pfizer came to help for FDA for that documentation. Who were Pfizer to meddle in the people's affairs? FDA is our department, and it is us and FDA's matter. Who is Pfizer to come into that? Ideally, there should be an arm's length between these guys, Pfizer's and FDA's. They came to become a party with them against us. That is how bad it is. So then the second thing government could have done was to create regulations, just like they have regulations for media, to say you would not stop this kind of discussion or that kind of discussion. But here the government itself sometimes offers help to create these anomalous censorships and weird things. Anyways, Colombian coffee bean. Is additional spike protein needed for the clot to continue to grow, or does the spike protein act as a catalyst for a reaction that continues without additional spike protein? So, in my opinion, it may not be that the additional spike protein is needed, and some permanent damage might occur. That is one. Now, people who continue to have the problem for months over months, there the spike protein pieces, maybe the S1 in monocyte is working. And that is why I drew this diagram. Maybe the spike protein is not there anymore, but anti-idiotype antibody or anti-ACE2 antibodies are present. They are acting as a spike protein proxy and behaving this way. Otherwise, yes, you would need the basic poison to do the work. Starfire says, I'm so happy that Luffy is safe at home. Thank you. But he is so annoyed. He does go out during the day, but he comes back very fast. And now he wants to go out at night. He would like to go out, but he's grounded. Sita says, soundproofing in case he complains while you're trying to sleep. Oh, he won't let me go to sleep before 10 until he's asleep. He sleeps in my room. And then he wakes up at 2:30 and just starts talking with me to say, go open the door. And that doesn't happen. So that annoys him. Margaret says, Texas Mac. Okay, so that's it. Thank you to Texas. Yes, Texas, thank you very much for your help. Correct. So Steve says, unfortunately, the government and media have become sales arms to pharma. Actually, it's very simple. Money. Wherever the source of the money is, there is the control. If the money is shifted to something else, then that would become the master. Okay, so let's stop for today. I have been spending my whole day on these topics. As you can see, the markings on them. I wanted to make sure I understand it. So, first, I actually thought I wanted to draw all these mechanisms, but there were so many mechanisms, so many papers that it was impossible to kind of put that in one talk. So, then I thought what is more important for us all, humanity in general, is the understanding of the problem, how to diagnose it, and how to manage it. That is the talk before this. This talk is more nerdy, scholarly talk between us to say, okay, now let's look at what they found. I really hope that Resia decides to join us. It will be so cool to talk with her. Okay, so with this, thank you very much. Please do me a favor. Please like, subscribe, and share. And if you would like to support this work as well, there are 3 links in the description. You can buy me a coffee, or you can become a patron, or you can use PayPal. Thank you very much, and I would see you tomorrow.